All right, hopping into chapter 4, chemical reactions and chemical quantities. Finally getting to do some more chemistry stuff. We talked about a lot of nomenclature last chapter, all stuff that comes into play on our nomenclature worksheet. We talked about things like what compounds? Ionic compounds. We had molecular compounds. We had acids, different types of acids. We had different types of ionic compounds. We also had some relatively basic organic nomenclature. I sent out an announcement, I believe, that talked about I screwed up some of the naming on the organic branched structures. I went back and edited the video. I just added in text because doing a voiceover would have been more work. So I added in some text. Basically, the Cliff's Notes version is for the alkyl chains, methyl, ethyl, propyl, etc. You're supposed to list those in order of alphabetical order. So ethyl would be listed before methyl. Ethyl would also be listed before dimethyl, even though dimethyl starts with a D. I think we go with the methyl part of that. Anyway, that was what I screwed up on that part. Shouldn't be a big deal for the class. And today we'll be getting into chemical equations and balancing and stoichiometry and fun stuff. So you may know that there's this effect called the greenhouse effect. So there are gases in our atmosphere all around our planet that are called greenhouse gases. And the reason they're called greenhouse gases is, like in a greenhouse, there's usually like some sort of a glass roof, walls. Light can come in and nourish the plants and give them energy. It'll also bounce off and hit the glass, and it might bounce back, or at least some of that heat is retained. So a greenhouse, you can get warmer temperatures, you can get sunlight to come through, and it helps warm the greenhouse. It also prevents some of that heat generated by the sunlight from escaping. We have gases in our atmosphere that do the same sort of thing. Light can pass through them, it hits the ground, it bounces back. Some of that, depending on how it bounces back, the energy that it has, will get recaptured by those greenhouse gases and released back to the earth as energy. And so it increases the amount of energy that we keep, and that can cause the temperature of the world to go up. So scientists have measured an average 0.7 degrees Celsius rise in atmospheric temperatures in the last 180 years, 160 years. Atmospheric CO2 levels have also risen 38%. And so if we chart atmospheric carbon dioxide and global temperature, we see correlation between these. Right? As the atmospheric carbon dioxide goes up over time, so does the global temperature. But just because two things go up at the same rate doesn't mean, or look like they might be related, doesn't mean that they are related. Doesn't mean that carbon dioxide is causing the increase in global temperature. But it is. There's some funny websites where you can look up, I don't remember what they're called off the top of my head, but it just picks two graphs and it shows you like, oh, these two things are related, and it'll be like trends in sale of UGG shoes and like rate of car accidents or something. And it's just like a silly website that shows you that two things that are changing in the same way doesn't mean that they're related. UGGs are probably not increasing the rate of car accidents. Anyway, that's a fun aside. The reason that we're talking about greenhouse gases is to talk about CO2. So CO2 is one of the greenhouse gases, carbon dioxide, and one of the sources of CO2 is combustion reactions, primarily from fossil fuels, so burning things like coal and gasoline and oil. It can also come from volcanic action. So how would we be able to tell if the CO2 from fossil fuels is a bigger contributor or a more important contributor than CO2 from volcanoes, since the Earth is also just producing CO2 by itself? So we would have to look at where is the CO2 coming from, how much is coming from different sources. And to do that, we have to analyze them with chemical reactions. So in a chemical reaction, we have one or more substances, our reactants, being converted to one or more different ones. So reactants turning into products. We can have one product and one reactant. We can have 2 and 1 and 1 and 2 and 2 and 2 and however many we want on either side. Our chemical reactions involve chemical changes. So we're going to have rearrangement and exchange of atoms. They get rearranged. We're going to have them moving around, swapping places, swapping partners, new bonds, old bonds, all that sort of good stuff. The atoms get rearranged. We don't destroy the atoms. They don't turn into different types of atoms. We just pull them apart, put them back together as something else. One particular type of chemical reaction is a combustion reaction. A combustion reaction is a type of chemical reaction where a substance combines with oxygen and it forms one or more oxygen-containing compounds. Often this is going to have the shape fuel, whatever the fuel is, methane if you're burning a gas stove, propane if you're grilling outside, octane and some other related compounds if you're driving an internal combustion engine vehicle. It's going to be fuel plus O2 going to CO2 plus H2O. That's what it's going to be a lot of the time. I think we'll see this again later, but that's the general form. We're reacting with oxygen. We're forming one or more oxygen-containing compounds. The number of compounds you have on the product side depends on what you put in. For the most part, in this class, it's going to have this form. The heat that's produced in combustion reactions, the drive that's produced in combustion reactions, is critical to the way that our world operates. So again, here's that chemical equations where we've got reactants going into products. Our reactants are on the left side, products are on the right side. We have some additional information. We've got these different abbreviations. G for gas, L for liquid, S for solid, AQ for aqueous, just meaning that it's dissolved in water. We saw this a little bit when we were talking about ionic equations. Anything that was AQ got separated out into its constituent ions. Equations are also going to provide us other information beyond just the formulas and the states. And not all reactions will give you the reactants and products in terms of their state. Some of them leave them off. We'll also be including the relative number of reactants and product molecules, or formula units, or whatever they are. And we can use these equations to determine the masses of the reactants and the products, if we know some of the other variables. So an example with combustion of methane. Methane's what we're burning typically if we're burning gas at home on our grill. Methane gas produces carbon dioxide gas and gaseous water. Whenever something burns or combusts, it's being combined with O2, usually just from the air that's around us. If we look at this equation, we've converted everything into their chemical formula. So we've got CH4 for methane, our O2, our CO2, our H2O. If we look at the number of oxygen atoms, we can see on the left side we've got 2 oxygen atoms. On the right side we've got a total of 3 oxygen atoms. This is bad. Why is it bad? They need to be equal. Why do they need to be equal? We cannot create or destroy matter. So matter must be conserved because of the law of conservation of mass. So we have to have an equal number of oxygen atoms on the left side as we do on the right side. Number of O on each side must be balanced. And we'll get into how to do that in a bit. I think we're now going to talk about the hydrogens being unbalanced. So we may also notice that on the left side of our equation, we've got 4 hydrogen atoms in our CH4. That 4 is because of our subscript of 4 behind the H. And on the right side, we only have 2 hydrogen atoms in our 1 water molecule. And so this equation violates the law of conservation of mass. This is not how things are actually going to be behaving. We're going to have different numbers of some of these chemicals. It's not just going to be 1 and 1 and 1 and 1 all the way across. So to fix those problems, we need to balance the equation. Balancing means make the number of atoms equal on both sides. Not the total number of atoms, although that will also be the same, but talking about specifically each of the elements. So the way that we balance it is by changing the coefficients. The coefficients are these numbers that go in front. So the 2 that we put in front of the oxygen, the 2 that we put in front of the H2O, those are coefficients. We can change those because that's saying we've got 2 oxygen molecules instead of just 1. We cannot change the subscript. The subscripts are these numbers that follow. In this case, it's 2s and 4s. The 2s and 4s are referring to the number of each of these elements in the compound. So our oxygen formula, we've got 2 oxygens linked together. If we change that to 4, that is no longer the same chemical. So it'd be changing the chemical. That's a completely different reaction. Also, O4 probably doesn't exist, or at least not for very long. So we're adjusting the number in front. We're not changing the subscript numbers because that would be changing the chemicals, and that would be changing the chemical reaction or the chemical equation in a bad way. All right, let's just see if we can do some counting. We want to count out how many oxygen atoms are on the right-hand side of the following chemical equation. So go ahead and give that a try. Okay, so counting up the number of oxygen atoms on the right side. The way that we do this, we're looking at coefficients times subscripts for each of our chemicals. I think I did coefficients in green on the last slide and subscripts in red. So for our Fe2O3, our iron 3 oxide, we've got 2 times 3, that's going to be 6. And we're adding to that the 4 times 2 in our carbon dioxide. So 4 times 2, that gives us 8. 6 plus 8, 14 oxygens. And we have to do that for all of the chemicals, however many elements we have on the left side and on the right side. Counting them up, making sure that they're equal. The steps that we're going to generally follow, the steps that I recommend following for most chemical equations, first thing that we have to do is write the skeletal equation. Reactants and products as chemical formulas. Like CH4 for methane. Sometimes we'll be given the chemical formulas, other times we'll be given the names, and we'll be expected to come up with the chemical formula based on the name, depending on the circumstances. Then we are going to start balancing things. So we want to balance the atoms, the element that occurs in more complex substances first. Elements in compounds on both sides. So if we've got a compound, a mix of multiple elements on both sides, and we've got an element that's in both of those, we want to balance those first, because when we change the coefficients, we're going to be changing the number of the other elements as well. And then we're going to balance atoms that occur as free elements last. The reason that we do this last, or sort of second in this case, is that it doesn't affect other elements. And we can use fractions for these. There are some occasions, some instances where it's convenient for us to balance a free element using a fraction in front of it. We will then get rid of those coefficient fractions by multiplying the entire equation to increase those numbers. And then our last step would be check everything. If we wanted to check things, we would count the number of atoms of each element on both sides. We just want to make sure that they're still balanced. We didn't screw anything up along the way. I'll give us a second more on that slide. All right, we want to write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. So we've got chemicals, silicon dioxide, carbon. We've got a key word here, to produce. To produce is where we put in our arrow. So we've gone from talking about reactants to talking about products. And our products are silicon carbide and carbon monoxide gas. Okay, so silicon dioxide, silicon, we're just going to have one. The di in front of the oxide means that we've got two oxygens. So this will be SiO2, and it's a solid. So we put an S in parentheses behind it. Our other thing that we're using is carbon as a solid. So it's just going to be C. Then we've got our reaction arrow, and we've got solid silicon carbide, which is just SiC. And we're going to also be producing carbon monoxide gas, CO, as a gas. Monoxide, so it's just one oxygen. That's the bad one. So this is our skeletal equation. And now we want to look at what chemicals do we have, what elements do we have in one compound on both sides.
It's not balanced.
Those are, so we have silicon, oxygen, and carbon. Those are our three elements.
Right.
Two of them show up in two compounds on both sides. So our silicon shows up in silicon dioxide and silicon carbide.
One is to balance it.
Oxygen shows up in SiO2 as well as in CO. So we're going to balance those first. It doesn't matter which one we do since they're just in one thing on both sides. So I'm going to start with the silicon. Silicon, on the left side, we've got 1 in our SiO2, and we've got 1 in our silicon carbide SiC. So that one's already balanced. And then we're going to balance our oxygen next. So our oxygen, we've got 2 on the reactant side because of our subscript of 2 in SiO2. We currently have 1 on the right side in our carbon monoxide. So that's obviously not balanced. Hopefully obviously not balanced. And so to get that to be balanced, we need to increase the amount of CO that we have. So we're going to put a coefficient of 2 in front of our CO, and now we've got 2 times the 1 oxygen for 2 oxygens. So now our oxygen's balanced. And the last thing that we're going to balance is the carbon, because the carbon is by itself on the left side. So if we look at the carbon, on the left side we've got 1. On the right side we have 1 in our silicon carbide. And we also have 2 times the 1 in our carbon monoxide. So we've got 3 carbons on the right side. We've got 1 carbon on the left side. We're going to need to add a coefficient of 3 in front of our carbon on the left side. And now we've got 3 on the left, 3 on the right. And we can quickly go through if we wanted to and check our silicon's still 1, our oxygen's 2 on the left, 2 on the right, and our carbons that we just balanced, 3 on the left, 3 on the right. So now we have a balanced chemical equation. Questions about any of that? Cool. Should be review from Chem 20. Another one. We want to write a balanced equation for the combustion of gaseous ethane. Ethane has the formula C2H6. It is also a component of natural gas, but it's a smaller component. And we're even told, somewhat generously, that combustion combines with gaseous oxygen to form CO2 and water, both as gases. So starting with our C2H6, it's a combustion reaction, and so it's going to be reacting with oxygen, going to form CO2 and H2O. And I'll go ahead and add in that they're all gases.
H2O is a gas. It's not liquid.
It's a gas in this case.
Okay.
Okay, first step done. We've got our skeletal equation. Second step, we need to balance things that occur in compounds. That's going to be our carbon and our hydrogen. The right side is only compounds. The left side, we've got our compound of ethane, and we've got molecular oxygen, O2. So oxygen is by itself on the left side. We're going to save that for last because we can change the coefficient in front of that. It's not going to affect any of the other elements, so that makes it a safe last choice. So balancing from left to right, for our carbon, we've got 2 carbons on the left side. And we've got 1 carbon in our carbon dioxide on the right side. To get those to balance, we're going to add a coefficient of 2 in front of CO2. Now we've got 2 carbons. Next up is our hydrogens. Our hydrogens, we have 6 on the left side because we've got 6 in each ethane. We have 1 ethane. So 6 hydrogens on the left side. We only have 2 on the right side. What coefficient do we need to put in front of our H2O
2.
to get them balanced?
2. No.
3.
3.
So we've got a subscript of 2. If our coefficient is 3, then that will equal 6. So 3 times 2 will give us 6. So now our hydrogens are balanced. We've got our 6 on the right, we've got our 6 on the left. And the last thing to balance is going to be our oxygen. So looking at our oxygen, how many oxygens do we have on the left side? We have 2. And on the right side, we've got 2 times 2 from our CO2. So that's going to be 4. And we also have 3 in our H2O. So we've got 7 on the right side and 2 on the left side. What can we multiply 2 by to get 7? 3.5 or 7 over 2. They're the same. So if we do 7 over 2, the number that we have is 2. So if you multiply the 2 by the 2 goes away, and then we're left with 7 oxygens. So whatever the subscript is, make that the bottom part, and then the target, make that the top part in the case of combustion reactions. So 7 over 2, 3.5, whatever you want to put there. And that balances it. Now we've got 7 on the left, 7 on the right. Can we have 7 halves or 3.5 oxygen molecules? No, why not?
Because there's no half.
There's no half, in the same way that I couldn't have 3.5 students in my class, legally. So how are we going to get rid of this 7 over 2?
Divide by 2. Divide the whole thing by 2.
You could add an extra one on the right side to H2O, add a 4.
This is where this step of if they contain coefficient fractions, clear them by multiplying the entire equation by the denominator of the fraction. It's part of why I wrote it as 7 over 2. You don't have to write it as 7 over 2. The goal is we want to get this, whatever the number is, 3.5 or 7 over 2, we want to get that to a whole number, an integer value. So 3.5 or 7 over 2, if you multiply that by 2, that would get it to turn into 7. We have to do that to both sides. We're going to increase both sides by the same amount, and that'll get us nice and balanced out. So we're going to multiply everything by 2, and then I'll rewrite it here at the bottom. So 2 C2H6 as a gas plus 7 O2 also as a gas goes to 4, because 2 times 2 is 4, CO2 also as a gas, plus 2 times 3 gives us 6, H2O, still a gas. And that would be our balanced equation.
So that one multiplies to the numbers in front.
Yeah, we multiply 2 to all the numbers in front. And then this is an instance where we would probably want to go back and check. I ran out of room, but we would want to check that we did everything correctly. So then check again that it's balanced. Usually we're going to encounter the type of equation, the type of reaction that we're going to encounter these fractions most is in combustion reactions. That's usually where they're going to show up. There is a way, there is a world, there's a time, maybe even, where we don't use the coefficients, but then you have to go back through and rebalance everything again. So this way is faster. It's just a little annoying maybe to deal with the fractions or the partials. Questions about that equation? All right. We can also do equations between ionic compounds, things that are double displacement or double replacement reactions, like in this one. So we want to write a balanced equation. We've got a reaction between a bunch of different compounds. So underlining all the compounds that we have there in green. And then our key words here, to form. To form means we've switched from reactants to products. So everything before to form, those are our reactants. Everything after to form is our products. So our first reactant, aqueous lead 2 nitrate. What does the 2 behind lead mean?
Lead, ferret. Oh, lead.
It's the charge. It's got a 2 positive charge. This is going to be PbNO3 2. We are also reacting this with, mixing it with potassium chloride, KCl, also aqueous. Then we've got our reaction arrow, and our product is going to be lead 2 chloride, so PbCl2. This one's a solid. And the other thing on our product side is potassium nitrate, KNO3. Skipping over the nomenclature part, how we got the chemical formulas, primarily to save time. But we figure out the subscripts based on what the charge is. Nitrate's a 1 minus, chloride's a 1 minus, potassium's a 1 plus, lead's a 2 plus, as it tells us in the equation. And then we have to balance it. This is a double displacement reaction or a double replacement reaction. So we're swapping the lead and the potassium, or we're swapping the nitrate and the chloride, whichever one you want to think about we're swapping. These ones don't usually follow our rules that we saw earlier very nicely. So for double replacement reactions, my recommendation is pick one chemical that isn't balanced. I'm saying chemical in this case because we have polyatomic ion nitrate. So what's something that's different on the left side versus the right side?
Not a nitrate.
Nitrate. Nitrate's different, so let's balance nitrate first. The reason that we're balancing nitrate as a whole intact unit is because it's a polyatomic ion. It's remaining intact as NO3 on both sides. This is faster than balancing nitrogen and oxygen separately, in that we just aren't writing them separately. On the left side, we have 2 because of this subscript in lead 2 nitrate. On the right side, we have 1 because we only have 1 potassium nitrate. To get those balanced, we need a coefficient of 2 in front of our KNO3, our potassium nitrate. What changed when we added, what other than nitrate changed when we added this 2 in front of KNO3?
Potassium.
Potassium. We're going to balance potassium next. Wrong color. So we're balancing potassium next. How many potassiums do we have now on the right side? 2. Because of this coefficient of 2 that we put in front of it. How many do we have on the left side? 1. To get those to balance, we need a coefficient of 2 in front of our KCl on the left side. So now our potassiums are balanced. When we added this 2 in front of our KCl, what's the other chemical that changed? Chlorine. So we're going to balance Cl next. So Cl, we've got 2 on the left side. How many do we have on the right side?
2.
Also 2, so that one's already balanced. A lot of the time this means that we're done. But we should still check our last chemical, which is lead, Pb. We've got 1 and 1. So we're going to pick, generally for these, this works. It doesn't always work, but a lot of the time it works for these. You pick a chemical that's not balanced, you balance it, you look at what was the other thing that changed. In this case, it was the potassium. You balance that next, and then once you've balanced that, we changed chloride, we balanced chloride next. This will usually end up getting you to the right answer in the fewest steps possible. So it's just kind of following, what did we screw up? All right, let's balance that now. That's my recommendation for solving these types of problems. Questions about those? Cool. All right, going back to our carbon dioxide question. The balanced chemical equation for fossil fuel combustion, oil fuel combustion, requires that we have the exact relationship between the amount of fossil fuel burned and the amount of carbon dioxide emitted. We're going to use octane as our representative fossil fuel. Octane is one of the main ingredients in gasoline. The balanced chemical equation for octane is here. You would be able to come up with this by yourself if we had octane. You could also just draw out octane and come up with its chemical structure or its chemical formula from that. What this tells us, what this equation tells us, is that we have 16 CO2 molecules produced, because they're on the product side, for every 2 molecules of octane that are burned. We can also ramp this up. Instead of just talking about individual little tiny molecules, we can do this at the mole scale. So this also applies to moles. 16 moles of CO2 produced for every 2 moles of octane burned. Or another way of thinking of it, 2 moles C8H18N goes to 16 moles CO2 out. We smash it up with our little hammer and then combine it with the oxygen in the form of combustion, and now we've got all these CO2 molecules that are out there. It's the coefficients, the numbers in front, that specify the relative amounts of each of the substances involved. And this is what stoichiometry is. Stoichiometry is the ratio of chemicals in a reaction. I'll write balanced chemical reaction. You can come up with any number of different ratios. In this case, we were looking at octane and CO2. We could also look at oxygen and CO2. We could look at oxygen relative to H2O. There's lots of different options. We just pick the one that we care about. So we pull out the coefficient that's going with the chemical, the coefficient that's going with the other chemical. Hopefully review from Chem 20. This requires us to go through thinking about the law of conservation of mass, which is why we are balancing our chemical equations and the number of atoms. Stoichiometry is just this looking at the ratio of the chemicals based on our balanced chemical equation. It's analogous to, usually the analogy is like some sort of food thing. In this case, we're going to be looking at pizzas. So if we've got all of our ingredients, we went to the store, or just we check our fridge, we're like, I'm really in the mood for pizza. I don't want to go buy Domino's or order out somewhere else. I want homemade pizza. We go and look in our freezer, our fridge. We know that we have to put in 1 crust, we have to put some tomato sauce, we got to add some cheese, and that's like the bare minimum for a pizza, assuming that we eat cheese. We'd probably have toppings, but regardless. So we've got 1 crust in, could equal 1 pizza out. If we have 5 ounces of tomato sauce, that's enough that we could make 1 pizza. If we've got 2 cups of cheese, that's also enough that we could make 1 pizza. But we have to have all 3 of these together, and we can express it mathematically using these using the colons. So 1 crust to every 5 ounces of sauce, to every 2 cups of cheese, to every 1 pizza. And we can pick out any 2 of those things that we want and use them to calculate something else. So we're going to look at how many pizzas can we make if we have 10 cups of cheese. So if I've got 10 cups of cheese, how many pizzas could I make with that cheese? What are the 2 things that we care about in this particular question?
The ratio between
Cheese and pizza. We're starting with cheese, we're going to pizza. So the 2 things we care about, cheese and pizza. We're going to pull those 2 ideas out and we're going to set them equal to each other. In theory, 2 cups of cheese equals 1 pizza. And there's a little bit of there's a caveat there, there's an asterisk there, because we also have to have crust and we have to have tomato sauce. And we'll talk more about those in a bit. But if I have 2 cups of cheese, I can turn that into a pizza with the rest of the ingredients. So if I'm starting with 10 cups of cheese, how many pizzas can I make? We can use this, 2 cups of cheese equals 1 pizza, as a conversion factor. For every 2 cups of cheese that we put in, we get out 1 pizza. We're using this as our conversion factor. We want to go to pizza, so the pizza part's on top, the 2 cups of cheese is on the bottom. That'll get the cheese to cancel. So cups of cheese cancel. The calculation that we're doing is 10 divided by 2. That'll give us 5 pizzas. This is actually, arguably, this is a more relevant calculation than most of the stuff that we do in the class. This is one of the applications of learning how to do the dimensional analysis and the stoichiometry stuff. You can also do this at home to inform your grocery shopping habits, perhaps. That same concept we can apply to chemical equations. So the ratios of the coefficients in a balanced chemical reaction, like this one below, also act as conversion factors. In this case, we're talking about moles of the reactants and products. We're specifying moles here instead of grams, because grams is just the mass, how much total matter is there, and moles is like how many pieces are there. And we care about the how many pieces there are. So we can use conversion factors to relate any 2 reactants or products in our equation. So if we burn 22 moles of octane, how many moles of CO2 form? The 2 things that we care about are what? The 2 chemicals.
Octane and CO2.
Octane and CO2. Those are the 2 things we care about, one that we're starting with, one that we're going to. We're going to pull those out and make our conversion factor. 2C8H18 equals 16 CO2. We are starting with 22.0 moles octane. The part of our conversion factor that needs to be on the bottom is the octane part. I'll go ahead and write in the moles. I often leave it off because it's moles on the top and the bottom. So applying the conversion factor would look like this. If we write the units out every time, and we remember that we have to cancel out units, we should never screw up putting our conversion factor in. Because if we put it in upside down, the units aren't going to cancel because we wrote our units out. And that would let us know we set it up wrong. We'll just flip it, and then we don't waste any time plugging the wrong numbers into our calculator. So moles, octane cancels. We're multiplying 22 and 16, and then dividing by 2. You should get 176 moles CO2. When we're considering significant figures, these numbers, our coefficients in our chemical equation, are exact numbers. They don't affect our number of significant figures. So we had 3 to start with, and we have 3 at the end. So coefficients are exact numbers in terms of significant figures. So this is just the stoichiometry step. We are almost never going to just do this stoichiometry step. We're going to be incorporating it into a larger equation. Typically, we are going to measure amounts of reactants and products in grams. It's not always going to be in grams, but a lot of the time it's going to be in grams. The stoichiometric ratios, the ratio of the coefficients in our chemical equation, only apply to amounts in moles. Coefficients only apply to or in moles. Because of that, we have to get to moles and then convert to the other moles, and then we can use mass again at the end. So this middle part, this is our stoichiometry step. Or our ratio step. I'll often just call it the ratio instead of our stoichiometric equivalence or some other thing like that, because really that's what it is. We're just looking at the ratio of the two chemicals. And we're tacking on now a molar mass conversion in the front, a molar mass conversion in the back. So our molar mass for A we're going to use in the front. Our molar mass of B, whatever B is, we're going to be using at the end. This is one of the general forms of calculations that we'll do in the class. There's other things that we can tack on instead of mass at the start or at the end, and we'll get into those details later. According to US DOE, the world burned this very large number of barrels of petroleum in 2013, the equivalent of approximately this many grams of gasoline. Calculate the mass of CO2 emitted. So we're finding mass of CO2 emitted using the combustion of octane as the representative equation. So the assumption that we're making is that our gasoline is all octane. It's not. That's the assumption that we're making to do this sort of rough calculation, rough estimate. So we're going to be starting with grams C8H18. Can we use our ratio from our balanced chemical equation with grams right away? We can't. What do we need to get to be able to use our ratio? What do we need to get to? Moles. Yeah. How do we get to moles from grams? Molar mass. So we're going to use molar mass to get to moles, C8H18. Now that we've got moles of octane, what are we trying to get to? What chemical are we trying to get to? Carbon dioxide, CO2. So we can go from moles of C8H18 to a different chemical, moles CO2. Our stoichiometry step is when we can change our chemical. And then from moles of CO2, can we get to mass of CO2? Yes. What are we going to use to get there?
Molar mass.
Molar mass. Right, grams CO2. What are the two chemicals that we care about in this?
Carbon and oxygen. Is it carbon? Oh no, it's I know it's oxygen.
C is carbon, O is oxygen. That's true.
Oh.
What are the chemicals that we care about for our
Oh.
calculation?
Hydrogen and carbon.
C8H18. What's the other one? CO2. I'm going to switch those colors. Those are the two things we care about. We're going to pull those out, and that's what we make our ratio with. So the thing we're starting with, the thing we're ending with, we pull out the coefficients with them. That's how we make our conversion factor. So our ratio step, 2C8H18 equals 16
That's what
CO2. That's going to be our ratio step, our stoichiometry step. This is what we're going to use to do the conversion. We're going to have to make a conversion factor form out of that. We're also going to need molar masses for octane and CO2. So I'll get those real quick. For octane, it's that number. And for CO2, it's this number with units of grams per mole. We take the number of each element that we have, we multiply it by its molar mass. For carbon, that's 12.011, so 8 times 12.011. For the hydrogen, 18 times 1.008. We'd add those two terms together, and you should get 114.232. If you don't remember how to do that, or you're a little fuzzy or unclear on how to calculate molar mass, go see Jonathan or Liz 12 to 5 in the STEM room, Tuesday, Wednesday, Thursday. Or you can ask me or look at past videos. So starting with 3.7 times 10 to the 15 grams octane. We are going to use our molar mass to convert to moles C8H18. So we have to use our molar mass number here. We have grams. The number part here goes with the grams. We're going to put the number and the grams on the bottom. We're dividing by our molar mass, is what that means. The moles flips up to the top. And we'll write the chemical in here just for good measure. So our grams of octane cancel because we've got one on the top and one on the bottom. The units that we have at this point are moles of octane, and that's what we wanted based on the solution map that we set out at the start. So we're on track. Then we have to use our ratio. Our ratio 2 octane turns into 16 carbon dioxide. We have octane. We're going to carbon dioxide. We're going to put the octane part on the bottom. I'll add in the moles unit there. And the 16 moles CO2 goes on the top. So our moles of octane cancel from the top and the bottom. We're now in units of moles CO2. According to our solution map, that's right where we should be. That's where we expected to be. So we're still on track. And then we have to use our molar mass to convert to grams of CO2. So we have moles. We want to get to grams. The grams part has to go on the top. The moles part would get flipped to the bottom. That looks like this. So moles CO2 cancels, and what comes out at the end is grams CO2. So we're going to multiply everything on the top. 3.7 times 10 to the 15 multiplied by 16 multiplied by 44.009. We're going to divide by the things that are on the bottom, the 114.232, and also dividing by the 2. You can do the top, multiply it all across, write that on the top, multiply the bottom all the way across, write that on the bottom, and then just do that division as one step. Also perfectly valid. And let's go ahead and do that way just to show it. I think I've shown that once, but another time doesn't hurt. So on the top, we would be getting this relatively large number. I'm going to invoke my ... my ellipsis, to say there's more stuff there. I'm saving room by not writing it out. On the bottom, 114.232 times 2, 228.464, and then we would do that division. We would be left with 1.1 times 10 to the 16, rounding for two significant figures. Questions? Cool. That's the longest way of writing it out, essentially. You can optionally leave off some of these units. Like for the stoichiometry step, if you want to leave off the moles, you can do that. For the molar masses, if you want to leave off the chemical part, you can do that. Just makes things not cancel out quite as nicely all the way through. So looking at the result we got the same one that was printed in the slide, which means we did it correctly, which is great. So petroleum combustion produces 1.1 times 10 to the 16 grams of CO2 per year. Volcanoes, they measured it, somehow estimated it, 2 times 10 to the 14 grams CO2 per year. Which one of those is bigger? Is it petroleum combustion or volcanoes?
Volcanoes.
Which one's bigger? Petroleum,
Oh, petroleum.
because it's 10 to the 16 versus 10 to the 14.
Okay.
So petroleum produces more CO2 by a lot. If my brain is working correctly, it's like 500 times the amount, 50 times. One of those two. That's cool. Yeah, so that's the conclusion of our CO2 conversation, essentially. This was just all that we were working towards getting. End result is the same as the spoiler that I said earlier. Petroleum's producing a lot more CO2, significantly more than volcanoes. Let's do the math. It's 55 times. Which means that the petroleum combustion is producing a lot more CO2. It's probably a much bigger factor than the amount that volcanoes are producing. It's probably not just like a natural Earth is going through a warming cycle sort of thing. It's probably anthropogenic or human-caused, human-made. All right, we've got a couple of practice problems. I'll run us through doing this first one, and then I'll give you some time to work on the second one. So magnesium hydroxide is the active ingredient in milk of magnesia. It neutralizes stomach acid, which is primarily the HCl part. According to this reaction, what mass of HCl in grams is neutralized by a dose of milk of magnesia containing this many grams of magnesium hydroxide? A couple of things that we want to look at really before we start the problem. Let's start off with, what are we given? What's a piece of information that we're given that is helpful for us for solving this problem?
The mass of the HCl.
Something given to us, not something we're
given.
finding.
Oh, the grams of the magnesium.
Yeah, we're given grams of magnesium hydroxide. What's another piece of information that we're given? The equation. What's something that we are looking for?
Balanced neutralization.
Mass of HCl. Right next to our question word, what? So what, and then usually the thing we're looking for is right next to that. So we're looking for mass of HCl. It specifies even in grams. is neutralized by or reacts with this many grams of magnesium hydroxide. We're also given a chemical equation. Is our chemical equation balanced?
No.
No.
It is balanced.
Is it? Yeah.
So it's a little more confusing because we've got hydroxide
Oh,
reacting
you're
with
right,
H+.
yeah. Yeah, it is.
It is balanced.
You move it into two.
The fast way to check if something is balanced, or one of the big key indicators that I tell people to point out or look at, if something's balanced, yes, it's balanced. The reason that we can reasonably assume that it's balanced, there's already coefficients. Nobody's going to give you coefficients if it's not already balanced, or they're mean. So typically, if you see coefficients already, it is balanced. Always good to check. But if there are coefficients given to you, it's almost definitely balanced. But it's still always safe to check. It's possible that somebody screwed up. If you're reading something out in the wild in a journal, it's possible that they screwed up their balanced chemical equation. Unlikely, but possible. So we don't have to do any balancing. That's awesome for us. So we're starting with grams, MgOH2, magnesium hydroxide. We are going to our final goal, grams, HCl. Can we do that in one step? No, but it would be sick if we could. But we can't do it in one step. What's the thing that we can convert from grams of magnesium hydroxide to? We can convert to moles. So we're going to convert to moles of magnesium hydroxide. Now that we've converted from grams to moles, what can we convert to? We just converted to moles, so we probably don't want to convert right back to grams.
Oh.
What's something else that we can change? Magnesium hydroxide.
Oh,
So we're trying to go from magnesium hydroxide to HCl. We can do that with stoichiometry. So now we can convert to moles HCl. We just changed chemicals and we've got the chemical that we want. Now we want to change the other thing, the quantity. So we can change from moles to grams. What are we going to use to do this magnesium hydroxide, or grams to moles for magnesium hydroxide? Molar mass. So we'll have to calculate a molar mass for magnesium hydroxide. What tells us a relationship between magnesium hydroxide and HCl? The coefficients in our balanced chemical equation. So the two things we care about, MgOH2 and HCl. So we're using the ratio here. It's 1 MgOH2 reacts with, we can write that as equals 2 HCl. And then we need to convert from moles to grams. What are we going to use for that? Also molar mass for HCl. Which should be 36.458. For our magnesium hydroxide, it's going to be 58.324. Questions about the solution map? All right, and then we're going to set up our calculation. I'm going to just rip through this to give us a little bit of time to work on the other thing at the end. So when you do this, it should look something like this. I'm doing the shortest version possible, so I'm leaving off some of the chemical units. And we'll go through and cancel stuff out. Grams HCl would come out at the end. Multiply everything on the top, divide by everything on the bottom, and round for 3 significant figures, 4.08 grams HCl. All right, and then we've got this one that'll give you some time to work on the rest of the class, I guess, to work on. I'm going to pick up next class on this slide, and we'll go through working it out. If you solve it in your spare time, in your free time, or other class time, the little red bar in the top right corner is just hiding the answer. If you go to the slides that are posted, they usually don't have that red bar in front of them or on them. You can see what the answer is supposed to be, but we'll go through the solution at the start of next class.